In my last video, we worked through a problem that started us off with a pressure cooker that was initially open, and then later on we closed it, that had both air and water inside of it. And we were told that given an initial temperature of 298 Kelvin and an initial pressure of 101.325 kPa, what would the final temperature of that pressure cooker be if we wanted the final pressure to be 200 kPa, given that the total volume of this pressure cooker was 0.1 meter cubed and the weight of the water inside the pressure cooker was 1 kilogram. If you haven't seen my last video, I highly recommend to go back and see the process of writing out all the equations to go into the pressure cooker and discover that the final temperature ended up being at about 366 degrees Kelvin. And if you have seen the video, remember that we used the n number of moles of water to help us discover that final temperature. Well, what if I said that we were doing the same problem, but we wanted to make it more interesting? Let's say we don't know what the volume of our pressure cooker is. That is an unknown variable. And let's say that once we achieved that final pressure of 200 kPa, we wanted the number of moles of our water that was part of the partial vapor pressure of the system to be equal to 0.3 moles. Well, that would make our problem a little bit more difficult, but I believe we can still do it using the same code that we wrote on our Google Colab Python in the last video. So let's try it. So you may be wondering, hey, why can we use the same exact code that we used for the last problem if we have a new unknown variable of the total volume of the system? Well, all of our variables, as you can see, are going to be staying the same except for the total volume of the pressure cooker. Our initial pressure, our initial temperature, our final pressure, and our weight are all going to stay the same. We're still dealing with air and water, so those properties stay the same as well. And the only thing we need to do is set up a new pressure calculation for the second problem. So let's go ahead and get started and do that. I'm going to be doing almost the exact same thing as the first time. So I'm going to be defining a new pressure calculation, press calc. I'm going to call this the second one, with the same array of x. There we go. I'm still going to be solving for the unknown variable of the final temperature. So temperature final is equal to, and what did I say up here? X array of the 0 variable. But this time I have a second unknown variable, and that's the total volume of the system. So V total is equal to X of 1. So those are my two unknown variables. I'm solving for the final temperature of the system, and I want to know the total volume of the system because that was not given to me in this problem. Next, I need to set up an equation for the volume of all of my vapor pressure. Well, how am I going to do that? Well, it's quite easy. Volume of my vapor pressure is going to be equal to the total volume of the system minus the volume of the liquid in the system will give me the volume of the vapor, because the only two things in my system are vapor and liquid. So if I subtract out the volume of the liquid, that will give me the total volume of the vapor. So the volume of my vapor is going to be volume total minus volume of the liquid. Well, I don't know the volume of the liquid, but I know the weight, and I can determine the density of that at a certain pressure, and I can also use the molecular weight, which will give me the volume. So I'm going to do weight of my water minus the number of moles of our water vapor, because some of that liquid water has evaporated and turned into vapor. So what do I want to call this? Number of water moles, so NW, that is now vapor. So NWV and that's going to be, I need to multiply that by the molecular weight. So molecular weight is P dot, I believe it's M, yeah, so there it is, MW, and yeah, but in units, I need to make that 1 times 10 to the third. Okay. Okay, divided by the density of my water, which I already did up here, which is rho, which is density at temperature, at a certain temperature. Well, here, I'm only focused on the final temperature, so I'm going to do P of rho L, temperature final. And there we go. I've set up an equation to tell me the total volume of the vapor in my system. What's next? Now I need to figure out the partial pressures in my system. There's going to be a partial pressure coming from the water and a partial pressure coming from the air in my system. So pressure of water and a pressure of air. We'll do the water first. It's going to be partial pressure of vapor, P vap right there, at that temperature final. And then partial pressure of the air is a little bit different. So that's going to be the number of moles in the air. So N air. And that's going to be times my R. So PV equals nRT. So number of moles, N, R, and then T. So temperature final, dealing with the final temperature here. And then all of that, PV equals, should be divided by RT. So R times, again, temperature final. There we go. So what am I left with? What's my return going to be? Well, my partial pressures of water and air, we know that, P of water plus P of air, pressure of water and pressure of air. If you set that is going to be equal to our pressure final. But if we want to set this equal to 0, then it's going to be pressure of water plus pressure of air minus pressure final. And then what else do we know? We know that the number of water moles as vapor is going to be at the end of our process. We want it to be at 0.3 moles. So our N number of water moles, NW, I call it NW underscore V, number of water moles of vapor minus some variable that's 0.3. What am I going to call that? I'll just keep everything simple. I'm just going to call it NWV 0.3. And that should be it. Shift enter, syntax error, 0.3. Oh, I guess it won't choose that as underscore. Okay, so it won't let me choose number of moles of water for the vapor pressure 0.3. I'll have to call it something else. I'll call it P3, just so I know exactly what I'm talking about. And I'll try it again. There we go, now it worked. So that's a crazy looking variable, but if you know what your variables are, it shouldn't matter. NW, number of water moles of vapor pressure, NW of vapor pressure, 0.3, and I need to set that equal to 0.3. And just so I remember, that's moles. So now I've defined the number of water moles of vapor that is 0.3 is equal to 0.3. Shift enter. There we go. So what's left to do? I've set up my calculation, or my second calculation. I've shown that my first unknown variable for the final temperature is the 0 number from that x vector. So that's my first unknown, the final temperature, what I'm solving for. My second unknown is the total volume, which in this problem we assume we do not know. And I've also said down here that something we do know that we didn't know in the last problem is that we want the number of water moles that are vapor to be 0.3. And I've set up an equation for the total volume of vapor in my system. I've also set up equations for the partial pressure of water and the partial pressure of air. So what's left to do? Well, I use my root tool. So root, and how did I do it up here? Root of, now I'm going to be doing root of this problem, pressure calculation 2. So I'm just going to copy this in here. Pressure calculation 2. And just like I had to do up here, my unknown was the final temperature. But here I have two unknowns. So I still need to provide a guess for the first unknown, and now I need to provide a guess for the second unknown. So pressure calculation 2 of, I'm going to say it's the same thing. I'm guessing for my final temperature, and I'm going to guess that it's 300 again. And now I also need to provide a guess for what I think the total volume is. Well, my total volume in the first problem was 0.1 meters cubed. So I'm going to guess that in this one, it's also going to be 0.1 meters cubed. And we hit Shift Enter, and here we go. It ran, and it gave me my x vector, the first variable and the second variable, which is what I asked for, TF and VT, the final temperature and the volume of the vapor. And it said that my final temperature is 3.39 times something to the second. So that's 393 Kelvin. Okay, that makes sense because I started at 298. I went up to a certain final temperature with a pressure of 200, a final pressure of 200 kPa, and it gave me a final temperature of 393 Kelvin. That makes sense. So I think that's correct. And then my second unknown that I was looking for was my volume total, because in this problem, I don't know my volume of the system. And this says it's 1.0 times 10 to the negative 1, which means that is 0.1. My guess was pretty accurate. So there I have done the same problem that I did in my previous video, except I had two unknown variables, the first of which being the final temperature, and now this new unknown variable being the total volume of the system. In this video, I will be going over the van der Waals equation of state and how it relates to a compound in respect to the critical pressure and the critical temperature of that compound. And more specifically, I will be going into the A and B parameters of that equation. But before I do that, I should go over what exactly a critical compound is. Well, if you think about any material in the universe that can exist in either a solid, liquid, or gas phase, they fall within this spectrum. So with pressure and temperature, they are going to either be solid, liquid, or gas. So as temperature and pressure increase, they can become liquid or gas or solid, depending on what the range that is. But when these two values become at a critical state, so incredibly high temperatures or incredibly high pressures, depending on what the compound is, it can exist in a state that is called critical. So it is above the gaseous state, above the liquid state. So when a compound reaches this state, it is almost undistinguishable between liquid and gas. So if you take water and you bring it up to a critical state, you won't be able to differentiate between it being liquid and gas. It'll almost look identical. So this can be important because any compound can be at a critical state, but different compounds exist at different critical states at different pressures and temperatures. But there's a way to find out how they relate to each other, no matter what compound that is. And we're going to be doing that using the van der Waals equation of state, because the van der Waals equation of state can be used for any compound. So what exactly is it? Well, I'll write it out. Pressure is equal to RT, that's 8.314 constant, times temperature, over volume minus B, minus A over V squared. T being temperature, V being volume, P being pressure. And then we have these two parameters that I mentioned earlier, A and B. And these are what we're going to be solving for so we can understand the relationship between pressure and volume at a critical state. And you might be asking, why do we care about this parameter and this parameter in the van der Waals equation of state? Well, if we take a look at another graph, we know that pressure and volume have a relationship together. And most of the time, they look something like this. But if we increase, decrease, or change that temperature, this relationship is going to shift. And it will continue to shift, depending on your change in temperature, delta T. So to understand that relationship between the pressure and the volume of your compound or of your substance or whatever you're looking at, you can use the A and B parameters to find this at critical points for your compound in a critical state. So how do we solve for A and B? Well, we're going to use derivations. So to make some room here, I'll take the first derivative of this problem with respects to volume, because remember we used pressure and volume. With respect to volume is equal to negative RT over volume minus B squared plus 2A over volume cubed. That's our first derivation. And if we do it again, we'll get the second derivation of pressure with respect to volume is equal to 2 RT over V minus B cubed minus 6A over V to the fourth. And this is our second derivation of the van der Waals equation of state. So now, we know as engineers that when you take the derivation of an equation, you're probably going to want to end up setting it equal to 0 and then adding on a constant. But in this situation, we can't do that yet. We can't just set these two derivations equal to 0. And the reason we can't do that is because the van der Waals equation of state and what we're deriving is in respect to when our compound is at a critical state. When it's at that state that's above the pressure and temperature of a compound that is beyond liquid or vapor. So our temperature and our volume and our pressure also need to be at a critical state. So I'm just going to do that by saying negative R times temperature critical, and then volume critical minus B, and then volume critical cubed. Same on the second derivation. 2 times R times temperature, critical, and then volume, critical, minus B cubed, and then volume, critical to the fourth. Now we can set these two derivations equal to 0. Remember, we're solving for the parameters of A and B for these equations. So now that we've set them equal to 0, let's begin solving for A and B. So we have two equations, two unknowns. First thing I'm going to do, because I see negative RTC over VC minus B squared plus 2A over VC cubed. I'm just going to make this positive and move it to the other side with 0. And I can do the same thing here because of negative 6A over VC to the fourth. Make that positive, move it over to the 0 side. So now I have these two equations. I can also make this equation a little bit simpler because 2 and 6, I can make that just 1 and 3. So I have 2A over VC cubed and then 3A over VC to the fourth. And then I have RTC, or R times temperature critical over VC minus B squared, and then RTC over VC minus B cubed. So they're looking pretty similar. So all I have to do, if I want to determine B, is multiply by the reciprocal, and I get B is equal to 1/3 VC. Just using basic algebra. And next, if I want to determine A, well, I can just plug B back into one of these equations. So I can take RTC over volume critical minus 1/3 volume critical squared is equal to 2A over volume critical cubed. You can see that. So this just becomes volume critical minus 1/3 volume critical. That just becomes 2/3 volume critical. If I'm solving for A, I'm going to multiply volume critical cubed over here. So then I just have 2A is equal to R times temperature critical times volume critical cubed over 2/3 volume critical squared. And if I just clean this all up, I get A is equal to 9/8 times R times temperature critical times volume critical. So now I've solved for my B parameter in the van der Waal equation of state and my A parameter in the van der Waals equation of state only by using some simple derivations in algebra to solve for these two. And now that means that whatever compound I'm using, if I put it in this critical state, I will know that the relationship of B is going to be 1/3 times the critical volume of that compound, no matter what compound you can think of that is in a solid or liquid state. And I can also know that the A parameter of that compound is going to be 9/8 times R times the temperature, the critical temperature of that compound, times the critical volume of that compound. So this can be immensely helpful if you're trying to understand the relationship between a compound, knowing its critical pressure and its critical temperature. And now we can know the B parameter and the A parameter of the van der Waals equation of state. So up next, in the second half of this video, I'm going to go into the compressibility factor of the van der Waals equation of state. So previously, I went over the van der Waals equation of state, P equals RT over V minus B minus A over V squared. And I showed you how to derive these two parameters of that equation, B and A. B being 1/3 of the critical volume, and A being 9/8 times R times the critical temperature times the critical volume. And the next step and the next component that I'm going to bring into this van der Waals equation of state is the compressibility factor Z. And Z is equal to PV over RT. So what exactly is the compressibility factor? Well, I like to think about it by writing out a real-world example. Let's say that you are given a compound, a certain amount of a compound, C, and you are being told that this compound that's either in liquid or vapor phase is being held at a specific temperature and a specific pressure. And your job as an engineer is to determine the size of the container that will hold this compound at this specific temperature and at this specific pressure. So volume determined. Well, let's think. This might be more difficult than it looks because we don't know exactly what this compound is. It's an unknown compound. And if it's water being stored at this specific temperature and pressure, it might require a different size container than, let's say, toluene or monoisopropylamine being stored at this temperature and this pressure. So the compressibility factor is a parameter that can be very helpful in determining the volume of a compound or the compressibility of that compound within a certain volume at a specific pressure and a specific temperature. So let's go through it and use the compressibility Z and the van der Waals equation of state to figure out exactly how that compressibility factor Z relates to a compound at a certain state. So here's our van der Waals equation of state. Let's make it so that it is at its critical state. And if you remember, the critical state of a compound is when it is at extremely high pressures and temperatures, and it is almost in between or constantly fluctuating between that liquid and vapor phase. So pressure critical, temperature critical, volumes critical. And the first thing I'm going to want to do is let's plug in these new values that we have for our A and B parameters. So PC is equal to RTC over VC minus B is 1/3 VC minus A is 9/8 RTC VC, so minus 9/8 RTC, VC over VC squared. All I've done is I've taken these parameters of A and B and I've plugged it into our van der Waals equation of state while it is at critical pressure, temperature, and volume. Okay, well, we have a VC up here and a VC squared here, so I'm going to get rid of this top VC. And then here, that's VC minus 1/3 VC. Well, that's 2/3 VC, so I can rewrite this as PC. PC is equal to 3RTC over 2 VC minus 9RTC over 8 VC. So we have RTC over VC and RTC over VC, so let's simplify this out. PC, make sure you can see this. Okay, PC is equal to 3 halves minus 9 over 8 times RTC over VC. And now from here, it's just basic subtraction of fractions. This will be the same thing as 12/8. And then we get PC is equal to 3/8 RTC over VC. Okay. Let's remember what the compressibility factor is. I erased it, but I'll write it again. Z is equal to PV over RT. Well, I have a P, I have a V, I have an R, and a T. So if I multiply by the denominator and divide by the numerator, I can get this to become PVC over RTC is equal to 3/8. So PV over RT is Z, so we can essentially say that the compressibility factor is equal to 3/8. So why is this important? Well, we're only dealing with variables here. We haven't put in any specific temperatures or volumes or pressures for any compound. So that means that the compressibility factor Z for any compound that exists as either a liquid or a vapor has the same compressibility as 3/8 while that compound is in a critical state. So if you put water into a critical state, its compressibility factor is 3/8. If you put toluene into a critical state, its compressibility factor at the critical state is 3/8. So that's why if you're designing a compound and you need to figure out the specific diameters or the volume of that compound at its critical state, so critical volume, critical pressure, critical temperature, you know as an engineer that its compressibility factor, the amount that that compound can be compacted, is going to be 3/8.